All right. Why isn't this turning on? Hey, let's get started. So we're going to briefly go over some phasors, and that was a good discussion from yesterday where we talked a little bit about Euler's identity. So we're going to do that again a little bit today. But there was one discussion about what a sine wave is or a cosine wave is. So the term that I use, and maybe I wasn't as clear as I could be, is a sine wave, right? Very different than the sine of an angle. A sine wave is something that varies with respect to time. And a pure sine wave has no DC offset, really smooth. And mathematically, we can represent that as either a sine wave or a cosine wave, right? A sine wave is just a cosine wave that is phase shifted by 90 degrees. So hopefully you feel comfortable either one of those representations. We're actually going to use cosines here because the math is a little bit easier to see with cosines than with sines. But you get the idea. So in the real world, there is no such thing as a phasor, right? There is no fixed voltage at a certain angle. But mathematically, and we do this all the time, we transform real world stuff into another dimension or plane, whatever you want to call it, to make the math a lot easier. For those of you who are in ECE, I don't know about Chemie if they do it, but Laplace is a perfect example, right? Because even our friends in math probably don't like to solve differential equations for fun. But if you do it in Laplace, it's a heck of a lot easier to do it, right? So you've just converted more complicated math into easier, more straightforward math if you can use the Laplace domain to do that. It's the same thing with phasor domain or steady state domain, AC domain, complex frequency domain, whatever you want to call it. It makes things a lot easier. So we're going to start off this class by looking at our two waveforms, voltage and current, and we're going to write them as having a magnitude and an angle. And the angle is not the phasor angle that we're talking about. It's actually the angle because there's potentially a phase shift. We started to talk a little bit about Eli the ice yesterday and how we had a current or a voltage would present before the other term. So we can do that here by adding in a phase shift. So we don't have to have a pure sine wave or a cosine wave that starts at 0. We can actually start at different times. And how we do that is we have a theta V and a theta I. Now, one thing about theta V and theta I, if you're in the real world, that theta V and theta I will never be outside the plus or minus 90 degrees. So if you've got 162 degrees for your voltage, you probably made a mistake, okay? So in this class, we'll never have wonky out of step numbers unless, again, we make a mistake. So we have a V of time, T or V of time, which is some peak value, we'll call it V max, times the cosine of omega T plus theta V. Here's where you have to be careful. If you're representing sine waves or cosine waves using this form, usually omega T is radians per seconds times second, right? And most of the time as engineers, we prefer to work in degrees. So if you're going to use the actual equation that we have here and try to calculate numbers, make sure you convert your phase shift or your theta V to actual radians per second, okay? And so oftentimes when I'm doing it, I will actually add the degree symbol next to the theta, the actual angle, so that I know that it's in degrees and it will remind me to convert it to radians per second. So just like the voltage, I have a current, and that has an I max, again, a peak value times the cosine of that same omega T. And this is really important. The voltage and the current have to have the same frequency. You can't have a current at 30 hertz and a voltage at 60 hertz. It's not going to fly. So your omegas are going to be the exact same values. And time, you're looking at any specific instant in time, so that has to be the same value. But your phase shift, your theta I, can be different, okay? Two very important things. The other important thing is in AC circuits, if we take them back and look in the real world, the only things that are going to have these time-varying quantities that's going to be rotating on the sine wave are these two, okay? These are the only two. You might start to say, well, what about power? Well, we actually change our term power a little bit. And so how we change it is we're looking at average power. So the voltage and the currents are always going to be an RMS quantity or a steady state quantity, but they're actually riding on this sine wave. Okay. And that's really important when we start looking at what we call phasors. Okay. But that's key is to understanding where the concept of phasors come in. For those of you who love math, right, we put the equation here to calculate RMS. So we want to use the term RMS, but we actually want to see where it comes from mathematically. So the root mean square of any sinusoid is you take the square and you're looking for the mean, right? I'm sorry, you take the square root and you're looking for the mean of that. So you integrate the sine wave, the square of the sine wave over one period, and then you divide that by the period. And that'll get you a Vmax divided by the square root of 2. That is the mathematical definition for calculating an RMS value for a sine wave form. We're actually going to take advantage of that term, and we're going to borrow the RMS term because that actual equation, we'll see where that Vmax over the square root of 2 comes in, okay? So remember that. We actually don't use this. We just want to show you where that is developed mathematically, and then we'll borrow it again in the future. So here's Euler's identity. Again, we went through that yesterday. Without a magnitude, well, there's a magnitude. It's just a magnitude of 1. So e to the j theta cosine theta plus j sine theta. If you haven't watched the lab yesterday, this is how you enter complex numbers with magnitude and angle in MATLAB, right? This is the only way that you can do it. So now we're going to go ahead and use our phasor notation and redo our voltages, but we're going to tweak it a little bit. Instead of calling it Vmax and Imax, we're going to use the square root of 2 times a magnitude of V, all right? And that magnitude of V is just some value that we come up with. So we'll call it the square root of 2 times some magnitude of V, and then we're going to extend that, and we're going to call that RMS voltage. We don't necessarily see why, or hopefully we don't necessarily see why, maybe you do, where that term RMS comes from, but it'll come back in a minute, or it'll hopefully get more obvious. All right, so we're going to use our Euler's identity. And again, engineers are efficient, lazy, depending on your perspective. So it's much easier to write V at an angle of theta using the bracket symbol, as opposed to writing it V e to the j theta, all right? Mathematically, the first phasor representation is the correct way to write it. But the second way, it's just hopefully more obvious. And I don't know, for those of you who've taken circuits through ECE, I don't know how they introduce the concept or even if they use the angle symbol. But in EET, we always use the angle symbol, which is just the bracket. But if you're a math major, that's how you did in ECE as well. If you're a math major or physics, maybe even physics, I don't know if they talk about it in the same way as AC circuits. They probably don't. But if they did, they actually might use the more mathematically rigorous approach of e to the j theta, right? So the reason why I'm pointing that out is it's neither one are wrong, but it's just a little bit more consistent with industry to use the bracket symbol, okay? So what we're trying to do is prepare people so that if you do decide to work on an industry and you see these, the likelihood of you seeing e to the j theta is about 0. I've never once seen e to the j theta in an industry document. Never. So here's our v of t. Now we're going to go ahead and write it to the time domain. And because we're talking a cosine wave, and we did Euler's identity, and we saw from here that the real part of this e to the j theta is the cosine term, right? And so since we're using cosine waves, we can see that if we take the real part of the Euler's identity, e to the j theta omega t, and e to the j theta v, we're going to get our voltage. Now, does anybody have any heartburn with the fact that I added on an e to the j theta? Because Euler's identity is here, right? It's e to the j theta term here. But you can see I added an e to the j theta and an e to the j omega t there. Anybody have any problems with that? The only reason why I did it is because I want to separate the two. The j omega t term is, we're going to see, we're going to take that away in a minute. but that e to the j theta term does not go away, all right? So we're just breaking up the exponential, right? Because it's e to the j theta, j omega t plus theta when we raise it to the power. And if you remember when you did exponents like that, you can just bring the term out and then just multiply the two, and that works perfectly fine. So now I'm going to go ahead and write my v as a full representation with a complex term. So I have the magnitude of v, cosine of theta v, plus j times the magnitude of v times the theta v. All right. And I can do the same exact thing for I. No difference. Again, the v and the I terms that I have here are RMS terms. Okay. I only added this part over here because I have that theta v. If it's purely, there's no phase shift with it, I wouldn't have to have a theta v term, which means it's zero. And e to the j 0, right, is 0. So I wouldn't necessarily need that sine term representation. Okay, so why do we do this? Well, because it really makes the work a lot easier. Remember Ohm's law? For a resistor, V equals I times R, or R times I, depending on who taught you. So in time domain analysis, I just take my voltage, or if I can find my voltage by taking my resistance and multiplying that by the current in any instant in time. So in phasor analysis, it's V equals R times I. Easy. So if I'm doing everything with resistors, I don't even have to do any work in phasor analysis because it's just multiplication. But as we talked about with Laplace, if we have differential equations we need to work with, let's simplify. So let's see if we can do that with AC circuit analysis. Well, an inductor is V of t, is the voltage drop across an inductor. It's equal to L di dt. But if I go in phasor land, phasors is e to the j omega L I. Wow. I don't have to take a derivative, do I? I'm just multiplying a bunch of numbers together. So why do we do AC circuit analysis? Because of that right there. I'm not solving differential equations. As long as I can do my work with steady state AC circuit analysis, then I can do it that way. Anybody know where I get the j omega L times I? That makes no sense. How does V equal L di dt become V equal j omega L I? Yes, sir.
I don't exactly what this one's, but I know that the impedance of the inductor.
Perfect.
You can replace the distance.
Yeah, that's exactly right. But where, so that was the impedance. Does anybody know the term impedance? How come the impedance of an inductor is J times omega times L? Let's do a little math. You remember V is equal to L di dt, right? If everything's in the time domain. Let's make I the easiest sine wave we can. So I of t is going to be equal to some current, I, sine of omega t, right? It's in the time domain. It's a real world sine wave. What is the derivative of I of t? Well, this is just a constant, right? With not time varying, so it doesn't change. And the derivative of sine is cosine. Am I done with my derivatives? Got to do the chain rule, which means I got to take the derivative of whatever I'm taking the sine wave up. What is the derivative of omega t with respect to time? Omega. But that is not in the sine wave, right? That is multiplying it out front. So di dt is omega I cosine of omega t. So V equals L times omega times I times the cosine of omega t. Uh-oh. Those two aren't exactly the same, are they? So did I make a mistake? One, no. I do make lots of mistakes. But did I make a mistake here? What's the difference between those two? They should be exactly the same, right? J?
The one on the right.
The one on the right is still in the time domain, but they should be able to be equivalent to each other, right? So if I wanted to go ahead and transform it, I would just take the average value of the voltage over one sine wave and do it that way, or the RMS value, I should say. But I'm missing the J term, aren't I? Or am I? It's a sine wave, right? It's an ugly one. What does a cosine wave equal to or look like? Something like that? What's the difference between a sine wave and a cosine wave?
They're attacking them.
90-degree phase shift, right? So if I take my equation over here and rewrite it as a sine wave, how do I do that? This is 90-degree phase shift, right? So don't I need to add 90 degrees in here? And if I'm using polar coordinate system, I have a real axis and a j omega axis. So if I want to put something on the j omega axis, how many degrees do I need to rotate here to get to the j axis? 90, because it's orthogonal, right? So I can convert everything into the phasor diagram except with this phase shift. How do I do the phase shift? JL omega I. That's where the J comes from. Because when you take the derivative of the sine, you get cosine. And because I can't take and figure out any other way of introducing that phase shift, because I did take the 90-degree phase shift, I must add the J term because it's taking the derivative of the current. So that's where the J comes from. It's the phase shift. Everything else falls out. But the J term sometimes takes a little more time to understand. Does everybody understand that? Because that's a huge, huge reason why, that's the only reason why J exists. If you don't understand where that J term comes from, it can cause a lot of confusions when you're starting to analyze circuits and say, hey, I have an RLC circuit. Why is it that I'm getting these phase shifts through the circuit? It's because you're taking the derivative of something or the integral of something and you're introducing a phase shift. Very, very important. Most of the time, if you were taught about impedance, somebody probably just waved their hands and said the J term was there. They might have derived where the omega term came from. But more often than not, people just say, well, there's a J term in here because we have to account for phase shift, and they never really show you. But it really is not that complicated. It's just the cosine wave has to be, or the sine wave has to be phase shifted by 90 degrees to get a cosine wave. That's the only reason. Okay. Capacitor is very similar, except it becomes 1 over J omega C times I. Now, these are all well and good. Let me give myself a little bit of room here. But this is not how I want to write it so it's generic. So I'm going to make a little tweak and say that for my phasor, I'm going to have V equals R times I. My V over here is going to be equal to J times XL, where XL is omega L, right? Got my I. And my voltage here is going to be X sub C times I. And I don't want to divide by J. I'm going to multiply by negative J. Does everybody know how you go dividing by J becomes negative J when you bring it up to the numerator? Multiply by the reciprocal. That's one way. I have 1 over J over here. If I want to get rid of it, what do I need to do? I multiply by J over J, which is J over J squared, which is J over -1 squared. which is J over -1, which is minus J, right? That's how you can go back and forth. So these are the ones that you'll use a lot more with you summarize that way, because we talk about an impedance. An impedance usually is a term Z, which represents the real and the imaginary part, but XL and XC are called reactances. Okay. They are reacting to either the current or the voltage that is going across or going through them, depending on your perspective. All right. So Z is impedance, X is reactance, and Z is a complex number. But it's not a sinusoidally varying number, is it? It's a resistance and an inductance. That's all. Okay, those numbers are fixed. All right, take a look at an easy example. I don't know what happened to my, well, okay, I'll just say my voltage is here, but I thought I had a figure that showed what it was. So V of t is 100 times square root of 2 cosine of omega t plus 30 degrees. That's feeding a 4 ohm in series with a 7.96 millihenry value. If I wanted to solve for I of t, right? If I want to solve for it, I can certainly do that, but here's my equation. If I use my KVL equation, I have negative V of t plus 4 I of t plus 8.96 times di dt. That's equal to 0, right? So not necessarily as easy equation, although this is just a first order differential equation. You could solve for it, but we actually don't need to do that because in AC circuits, we oftentimes are only looking at things on an aggregate or an average. There are times, and if you remember on our second class where I showed a diagram showing the different times, we actually don't care about things happening on the time domain. In many of those cases, we're really interested in things on a steady state. So we're going to get rid of this, and we're actually going to do things actually with phasor analysis. So we've got to know the frequency, which is 60 hertz, because that impacts the DIDT. And we're going to convert our inductor over here into a reactance, an XL. So XL is equal to omega L, which is 2 pi times 60 times 7.96 milli. And when I do that, I end up with 3 ohms. Okay. And it's J3, not negative J, positive J is what we saw on the previous slide. So now we've got our XL or JXL over here. This is just a resistor. This has to be converted to a phasor. And the, yes? Oh, yes, because I made a mistake. As I said, I make mistakes, right? So that was a mistake. So now I can go ahead and I can just do my equation, and I can do V now as a phasor. What's that?
Where does
Where did the J?
J3?
Yep, I'm going to show you here. That's the reactance that I need to get from an inductor. So I need to get omega times L. So that's 377 times 7.96 milli. And then I have to add the J, whoops, I have to add the J term here after the fact, because I've got to account for the fact that it introduces a phase shift. So anytime you have a reactance, you either need to include a positive J or a negative J, one of those two. Go ahead.
The resistor is omega L.
No, there's no space here. There should be a space. Let me see if I can make the space here real quick. Get that out of the way. So this is, why is this converting? Oh, it's a picture, but it should be just an equation. So I'm not sure why. These are all equations. Oh, there we go. So How's that? Sometimes conversions and stuff like that in Microsoft Equation Editor can get a little bit weird. And so that's why there was no space. So R is just equal to 4 ohms.
And then the answer is 3, not 3J.
No, XL is equal to 3, but when you make it an impedance with an actual ohm value, you have to include the J term. Okay. All right. So there's a bunch of different ways I can do it. What I've shown you over here is finding the combined impedance. You also can do it this way. So negative V plus 4I plus J 3I is going to equal 0. Now I'll substitute my voltage, which I converted from time domain quantity to a phasor quantity. So I have negative 100 at an angle of 30 degrees plus 4I plus J 3I is equal to 0. So I is equal to 100 at an angle of 30 divided by 4 plus J3. And if you stick that in MATLAB or in your calculator, you should end up with 20 at an angle of minus 6.9 amps. If you want to bring that back to the time domain, all you need to do is multiply the 20, which is an RMS value, multiply that by square root of 2, and then we're going to go back to either a sine or a cosine wave. We'll add in our omega t, and then we'll subtract, or we'll add in the phase shift, which in this case, it's negative 6. Okay. Questions on that? Make sense? Yes, sir.
Sorry, I think I missed where we got the first equation, the negative DMT plus.
Right here?
Yeah.
It's just a differential equation. We applied KVL in the time domain. We wrote a differential equation to do the loop equation all around the circuit. Everybody remember, know KVL? I'm not sure how many are ECE versus ME versus CIV and Chemi. There's a lot of different majors, but hopefully you all were approach or discuss KVL. I think that's even in physics, right? They do KVL loop. A KVL loop essentially is just conservation of energy. If I start at this point here and I come all the way back to that point, there should be no potential difference between that point when I started and when I ended. It should be at 0. So that's why you say the sum of the voltage drops equals 0. Good question. Any other questions? Yes, sir.
The angle, how did you find it? You've got arctan, reverse tan, or
You can do arctan, or you can use MATLAB, and you can just do the calculations, and it'll give you the angle automatically.
so which formula should I use?
You can use whatever you want.
Oh,
Either one is the same result. This one gives you a Z magnitude and angle. That's using polar coordinates. In rectangular coordinates, it's 3 plus J4. Do you have a question in the back?
Yeah, could I use the polar function in the calculator?
Yeah, that's perfectly fine. If you use the polar function in your calculator, it basically is putting in e to the j theta for you. Yep. But behind the scenes, what your calculator is doing is converting everything to the rectangular mode and doing all its calculations anyway. So it's doing the same, basically the same process. Other questions? I have a question for you all. Is Eli satisfied? Are they content? Are they not content, or are you unsure? Couple of thumbs up. Anybody thumbs down? I forgot. What does Eli say? Be careful. You're right. So for those of you who didn't hear, he said voltage leads the current in an inductor. Yes, but you're using the word leads, and we're going to reserve that word a little bit later on. Leads and lags is going to mean very different to us. So if you remember what we talked about in lab, I said the voltage presents before the current. Okay, I'm trying to be very, very, very consistent with my terminology because hopefully by hearing it over and over again, you'll see that leads and lags means very different things. So does it present? Well, the voltage is up over here at 36.9, and the current is down here. So is Eli content? I think so. Because I see the voltage and then I see the current. So everything checks out okay. All right. So now we got to do some power. Because voltages and currents, we can do that pretty easily. But the power is where we get into problems, where we actually have to make some tweaks to our equations. Mainly that whole RMS stuff. We started talking about RMS and we introduced the square root of 2, but the problem is we didn't really say where it came from. So now we're going to tell you where it comes from. So my power, there's only one type of power, and it's real power. Real power is an instantaneous term. You probably have never seen the P of T expression, but it's at any instant in time, the power for a source or load at that instant in time is that voltage times its current at those same values of time. So we're going to plug in our V of T and our I of T that we developed before. And this is why we use the cosine waves, because we have a trig identity that makes it much, much easier for us if we use cosine waves. And I showed that trig identity there because I can never remember it. You all can remember that. That's really impressive, but it's a lot for me to keep track of. But anyway, that's the beta term for the cosine A times alpha times cosine B. And when I plug those in, I end up with 1/2 V max, I max, cosine theta V minus theta I plus cosine 2 omega T plus theta V plus theta I. Okay, when I multiply it out, that's what I get. So at any instant in time, I can do this calculation here. But I don't want to do this. In steady state, I don't look at time wave, sinusoidal waves. I look at things over a cycle, essentially over one cycle. So I would like to convert my P of T to an average power. Okay. So just like we did when we calculated RMS, when we were looking for the mean, we're going to go ahead and look for the mean here. And so what we see is when we integrate our power of time waveform over one cycle, what happens? We end up with VI cosine theta V minus theta I. What happened to the cosine 2 omega T plus theta V plus theta I? Doesn't that have an integral? Yes, no? Anybody? Why did it disappear? Because clearly I can see that this part over here looks like it's copied over here. That term is gone from the final answer. Why is that? Any guesses?
It's possible it came up to 0. Still figuring out why. That would make it disappear.
Yep. Let me ask you a question. If I asked you to integrate that over one cycle, a cosine wave, what's the average value of a cosine wave? 0. Isn't this a cosine wave whose frequency is 2 omega T that's been phase shifted a little bit? So instead of something like that, let's say it looks like that. Still a cosine wave. Its average value is 0. Because of that part right there, it's an actual cosine wave. Remember how we talked about this at the beginning of class in lab? I said a waveform versus a cosine of a number. Omega T is a waveform. We know that average value is 0. This Does that have time in it at all? Those are numbers, those are fixed. So this is, I don't know, 0.75, right? 0.23, it's a fixed number. So the average value of a fixed number is that fixed number. So that's the reason why those terms don't disappear, whereas the cosine of 2 omega t term disappears. So good, I've got this term over here. How did I do that? I really have this, right? Correct? That's what I integrated out and I ended up with. But how did I end up with that magnitude V, magnitude I, which we talked about as RMS before? How did I get those from here? Well, I love me some math. 1/2, I can also write it as right? Square root of 2 times the square root of 2 is 0.5. Anybody doesn't believe me, try it in your calculator. Now I'm going to distribute my square root of 2's. And I'm just going to be lazy and call it theta VI. That's why. So that whole thing that we called RMS was just a whole mathematical calculation. For us, it's just a nice, convenient way to distribute that 1/2. Our work requires us to have a 1/2. But in actuality, we can distribute it and just call them RMS terms. So why do we calculate or convert to RMS? Just to make the power equation work. We're looking for the average power over one sine wave. And if we use the peak values, it's not going to give us the calculations we need. But if we use the RMS values, our results work out. So the use of the term RMS is just a simplification to say divide by the square root. So if I plug in my laptop here, which I did, I'm not seeing 120 volts. I'm seeing a sine wave that varies between plus and minus 167, right? But because I can't make my calculation work by using that plus or minus 167, I just say that that plugs in at 120 or 240 or 277 or 480 or 345 kV, right? Which again is the highest voltage, line-to-line voltage in New England, not counting DC. I always thought that was pretty impressive when I finally figured that out, saying, aha, why did everybody call it RMS? It never made any sense to me. It's just because your power equation, that's the only way it works out. I don't know, you might find this useless information, but sometimes I always like to give the background story as to where things come from. It's just from there. So RMS it's really not doing RMS. It really is just to make this equation.
So it's just for the 1/2.
It's 1/2. That's all it is.
That's why we're using it.
That's why we use it. Not once did I go through here and say, hey, folks, let's do this equation here on the bottom. Did I? I never took the square of the voltages and then integrated it over one period and did all that. Not once. But I did use the fact that I divided by the square root of 2. So you know what? Let's call that RMS. Thumbs up. They could have called it anything. They could have called it B, Barzillai if they wanted to, but they decided to go ahead and do it that way. Okay. So that is our average power calculation. P is VRMS times IRMS times the cosine. And here's the key thing. This is another key thing. There's a lot of key things here, but it's the difference in angle between the voltage and the current. It's not the addition, it's the difference. And we'll see why we need to keep that difference following through as we work through this. So power has a real part, right? It's consuming load, but we also talked about that reactive part, right? That's the borrowed power. And we can't just ignore that, because what happens in real time is, well, let me actually bring it up. I developed this a little while ago. So let me I wrote a simple MATLAB script file that I generated the figure on, but let me do this one. It's over here. Where is it? Is it this one? Oh no, this is the one we did in lab. I'm sorry. This one. Like I said, I apologize. I should have had MATLAB running, but I didn't, so it'll take a second. And essentially, depending on what that phase shift between the voltage and the current is going to determine how much power has to go out to set up magnetic and reactive or magnetic and or the static, right? The ones that are on the capacitor, those two, it's electrostatic fields, so the magnetic and the electrostatic fields. So you can allow the capacitors and the inductors to do their things. So at some points in time, you have to put power out on the system and you have to take it back because the magnetic fields and the electric fields are not using it. They're sending it back and forth. And why do we need to account for that? Because the current going out on the system, its magnitude has to be greater to be able to take that current back and forth. Okay. So it has a pretty big impact. All right, so I'm going to close that one and hopefully this launches. I think this is the right figure. If it ever launches. And so while we're doing this, and while this is chunking it up, what would be, oops, we don't want this one. That's the Z-bus one. Where is the, sorry. You must have called it something else. This one? No. Oh, that's why, because I don't have all the, I gotta click up the types here. I thought I had all the MATLAB stuff all sorted, so. We don't want synchronous. Where is it? It's not Newton-Raphson. It's not that one. Not that one. Darn it. Sorry about that. Having a hard time finding the problem. Well, I'll find it and I will try to put it back up. But essentially, what it does is, why isn't that PowerPointing? But essentially what it does is, depending on the phase shift, you actually will have some negative power that has to go back to the system. So if the phase shift is 0, right? If there is no phase shift between voltage and current, what type of load would you expect it to have? If there's no phase shift between the voltage and the current? Purely resistive, right? So if there's no phase shift, the load is purely resistive. And how much power is being stored in a resistor? None, right? It's all being dissipated. So there's no fields that you can store it. So all the power that goes to the resistor is dissipated. None has to come back. If it's slightly capacitive, right, which means if the current presents before the voltage, then that sign term, that sine of theta v minus theta I becomes a negative. It's a sign of a negative number. And now you actually have to send some power back. And so what you'll see is when you multiply out in the time domain, you'd actually see the power, some negative power that has to go back to the grid. Same thing for an inductor. So we're going to rewrite these two terms. or the S term, which is now going to be our total or apparent power, which is going to be a combination of the real power plus this reactive power, that borrowed power that has to get sent back. And that's P plus JQ. I also can call it V times I, and it's the conjugate of I. Why do I put the conjugate of I in there? Well, we know it's V times I, right? That's the V times I, which has V at an angle of theta V and I at an angle of theta I, right? So if we multiply those two together, what would we end up with? V times I, theta V plus theta I. Is that correct? Is that what we have for power? Don't we have a minus theta I? So how do you make this angle right here negative? You take the complex conjugate of it, right? So this term right here is the complex conjugate. And when you do that, that becomes a negative number. All the complex conjugate does is take a negative of the J term, which means it takes the negative of the angle. So you need to highlight this in your note that it's the phasor V multiplied by the conjugate of I. If this is not clear enough, do this. Put it in parentheses. I think in terms of order of operations for math, I think if you raise it to an exponent or like take the conjugate here, that would be a higher mathematical property, but the conjugate is kind of an odd term, right? We don't often see it. So you can just put it in parentheses there and you can do it that way. Units. Real power is joules per second or watts. Reactive power, well, that's a new term. So we're going to just call it volts times amps, and we're going to call it reactive. So that's bar. And then the total power, which is the addition of the real power, watts, plus the reactive power, bar, we're going to just call it VA, or volt amperes. And because engineers like to make things hopefully easy, this is my P, that's my Q, that's going to, let's say it's going to a load. So the total power is the vector addition of those two. And I can go ahead and calculate theta here, or somehow come up with a calculation for theta using SOHCAHTOA, right, as equal to P over S. SOHCAHTOA is the adjacent over the hypotenuse, P over S. So the cosine of theta is equal to P over S. Isn't P over S a ratio of real power to total power? So how much the total power is real, that's a useful quantity, right? Because if I'm only getting paid and how many joules the customer is consuming, I want my ratio to be sky high. What's the highest ratio that I can get for my ratio for P to S? Yes. So your power factor, and we'll talk about where we talk about that, will never exceed 1. Yes, sir. And it can never be negative. Yes. The Q can be negative, but the power factor can't be negative. And that makes sense, right? Because S equals P plus JQ. So how could P over S ever be greater than 1? Can't, right? So the term P over S is the ratio of real power to total power. Engineers like to be efficient, so we just called it the ratio of power. And back in the day, ratio was called a factor. So now we just call it power factor. So the term that you will use all the time is power factor. And it's not a positive or negative power factor. It's leading or lagging. So remember when you said at the beginning of class, when you used the term, I think it was leading, those terms are reserved for us. Leading and lagging is what is the current doing? is the current leading or is the current lagging? And why am I harping on this? Because I know a lot of you aren't going to work in the utility industry, but if you work in renewables and you kind of try to connect to the grid, you'll often come across the term, my inverter-based PV system can operate at a 0.95 leading or lagging power factor. That's just what it is. That's the industry term. So if you want to work in renewables and you want to connect to the grid, which almost all renewables should be able to, that's what the inverters are rated for. They'll tell you a power factor and they'll tell you if it's leading or lagging. So there's a lot of electrical specifications on an inverter, right? And these are pretty darn important. So understanding who or whom is leading or lagging is the biggest thing. So it's always current. What is current doing? Is current leading or lagging? That's it. And since my current lags an inductor, lags the voltage in an inductor, I like to say when I run this through my S equals VI machine, because I'm taking the conjugate of I in an inductor, I end up with a positive Q. So from the perspective of it's a load, positive P and positive Q are going to a lagging power factor. That's most real world systems operate that way. If it's a leading, so this is lag. If it's leading, lad, then the voltage is down here and the current is here. So when we draw that, my Q is going negative. So in a leading power factor, the Q is actually in the opposite direction. So here's the really confusing thing about load. When we think of load, we always think about absorbing power. Yes, it is always absorbing real power, but a load can be absorbing or supplying reactive power. It can go in or it can go out and it still stays a load. Same thing as a generator. It can go in or it can go out. So it's really helpful if you draw, let me put up this real quick. If you draw a box and if you say it's a generator, we say P is going out. If Q is going out, then it matches our lagging power factor, right? So this would be lagging, gen or a source. If it's leading, we have our box. P is going out because it's a source of power. But now Q is going in because our power triangle does something like that. If it's a load, so these are sources or generators. If they are loads and I have a lagging, P is going in and also Q is going in. Because what I've done is I've just dictated that P is always in the positive direction. You always are in quadrant 1 or 4 in your XY coordinates or XY plots. So P is always a positive number, but Q can be a negative number. So what I see here is both P is going in and Q is going in. So this is a lagging load. If it's a leading load, P is still going in, but now Q is going out. So this adds a lot of complication because when we think of load, we think we're always pulling stuff in, but not Q. Q can be in or out. Many, many, many loads can be providing Q if they're capacitive, right? Remember the ice part? The ice part is a leading, because current leads the voltage, and a capacitor. So Q is going to be the opposite direction. So interestingly enough, if I'm a load, if I'm a leading power factor, the Q is actually going out and supporting the grid. If I'm a generator and I'm a leading power factor, I'm sucking Q from the grid. I'm actually pulling Q off the grid. And sometimes you need to do that. At night, when the transmission system is pretty lightly loaded, your voltages tend to be really high and your current tends to be pretty low. Well, because you've got basically big capacitors, right? If you think of wires and they're energized, then they are basically large capacitors. So overhead system at night can put out a lot of reactive power. And so then you have to operate the grid at a lagging, or the generation in a lagging power factor mode. That's why the inverters, remember I said they can operate in leading and lagging power factors? Because the grid demands it. There are times when you'll have to operate. And if you can't operate at a lagging power factor or a leading power factor, you know what you need to do? You need to adjust your output until you can. So you know what the worst thing you can do is if you're a generator, I've got all the sun in the world, I'm ready to turn on my PV and crank out 4.99 megawatts and run it until so I can make so much money. And then the utility calls you up and said, well, you got to run at a 0.95 lagging power factor or leading power factor. Oh, I can't do that. My one only goes to unity. Well, you have to back your output off until you can meet those requirements, which means they have to shut down. That is a requirement of the grid. If you want to be able to interconnect to the grid, you better be able to operate at those constraints. If you're in New York City, it's even worse. I think Con Ed, which is the utility for Con Ed, I think they mandate 0.85. Very, very restrictive there, but they have different problems because they have a lot of underground cable. So reserve leading and lagging for current. What is current doing relative to the voltage? So again, you can do Pythagorean's theorem and Euler's identity to go back and forth. It's totally up to you, but your calculators or MATLAB can do it all day. Here's a simple problem. And this is typically what you're going to find in industry. You have a load that's written as power, 100 kilowatts, and it has a leading 0.83 power factor. What is the phase angle, the power factor angle, and what is Q and what is S? So first thing I do is I take the inverse cosine of 0.85 and I get 31.8. And the reason why I put a negative there because it said it's a leading power factor, which if you remember the power triangles, if it's a leading power factor, P is positive, but Q has to be negative. So all I'm going to do for problems is I'm going to tell you I have certain power factor and it's leading or lagging. You're going to have to be able to figure out, do I put it as a negative number or a positive number? Okay. So you got to start getting comfortable with the fact that you're going to be able to determine it, because inverse cosine of 0.85 is never a negative number, is it? It's always a positive number, but you got to be able to put in that negative term as necessary. And then it's totally up to you. You can use magnitudes, you can use whatever you want, but we can see that S is 100 kilowatts over 0.85. So I'm basically using the SOHCAHTOA trig identity to go ahead and calculate S, right? Because P over S is equal to the cosine of theta. I end up with 117.6. And then over here, I use the trig identity for the sine term, right? Which is the opposite over the hypotenuse, because I know what S is. So I just take the sine of the angle, multiply it by the hypotenuse, and then I get the K bar, which again is a negative number. And so then I could build a power triangle. This right here is equal to 100 kilowatts. This right here is equal to minus 62. And this right here is 117.6. And then I'll just add in the angle over here for that. And all power triangles are right triangles. All power triangles. There's no, in this case that, sometimes you get those trick questions on tests. Are they always the case? And almost never say yes. You never say that they are always the case, because there's almost always at least one instance when they're not. This is the one time that you can say, yes, all power triangles are right triangles. 100%. Okay. So last couple slides before I do that, questions on this, because we've just covered a lot of potentially challenging material that is really kind of maybe flipping a lot of perspective, particularly for ECE students, because we haven't seen a lot of power stuff, but we have to do that if you're working in the utility world. There's no if, ands, or but about it. If you can't do power factor, power triangles, leading or lagging, RMS quantities, phasors, phase angles, you really are going to struggle. So what we did in the last, hour or so is really like what you absolutely baseline need to be able to at least be remotely, understanding the utility industry. It's the bare minimum. And if you took a renewable energy class with me, which probably you may have, we touched on it by that much because you can't get into too many details because people get confused really quickly. And in that class, we only touch on it for a moment because, again, just to give you a flavor of leading and lagging. But over here, it's worthwhile to understand it because the hope is you're going to get a little bit more in depth being able to understand that. But every wind turbine generator, every inverter, every hydroelectric facility, every fossil fuel, nuclear, whatever technology you have, if it's going to connect to the grid, you're gonna have all this information. You look at the nameplate, it's gonna have power factor, it's gonna have voltage, it's gonna have rating. Usually it's a watt rating or megawatt rating. And those are kind of like the baseline pieces of data. You'll also have some impedance data on it too, but sometimes that can be more, detailed. So usually you need a data sheet. Okay, questions? So far, so good?
I have a quick question.
Yes.
For the complex power, I guess I just didn't understand. Maybe you could go over it one more time. The conjugate of the current for the voltage times the current equation.
Yep. So you're kind of breaking up a little bit. I'm not sure if you were continuing to talk. I apologize if I talked over you, but there was quite a bit of static. So S equals VI conjugate. The reason why we need the conjugate, because my real power term, if you remember, was VRMS times IRMS. And the angle, well, actually, you took the cosine of the angle. The cosine was of the angle associated with the voltage, and you subtracted the angle associated with the current. So if you just took VI and multiplied those two together, you would add, if you remember from when we did polar numbers, when you multiply two polar numbers, you multiply the magnitudes and you add the angles. We have to subtract the angle. So the conjugate forces the angle on I, the current I, it forces it to be a negative number. So when you do your voltage times the conjugate of the current, you end up with magnitude V times magnitude I. That's still the same. But then it becomes a cosine of theta V. And because you take the conjugate, minus theta I. Okay, does that answer your question?
Yes, thank you.
Okay. Perfect. Oh, so last little bit of this class is going to set us up for the next class. When we do Y-bus, we're going to come up with a very simple way to solve systems, very efficient way, I should say, maybe not simple, but efficient. But it's all going to be based on conservation of power, which some of the real power into a node has to equal 0, as is the case of reactive power. So we're kind of setting up a little bit where we're doing KCL, right? Because we talk about a sum of a current into or out of a node. That's the definition of KCL. And so we know that we have our S equals VI conjugate. So S in has to equal S out as well. So let's do an example over here where we took our case where we said our current in phasor land or steady state analysis land is 20 times at an angle of minus 6.9. If we do the S equals VI conjugate calculation for the power supply, we end up with 2000 at an angle of 36.9 VA. Our angle with S is 36.9. We take the cosine of that and we end up with a 0.8 power factor. How did I know it was lagging? Can you see anything on here that tells me it's lagging? Anything there? The voltage is positive. That almost tells the story. Is negative?
If it's negative, then it's leading.
You're both kind of saying that you're close. Alan? That's part of it, but the real reason is the voltage is here and the current is here. The current lags the voltage. So everybody was kind of saying that they were close to saying the whole thing, But really what I was looking for, it wasn't the fact that the angle was negative or that the voltage was positive. It was the fact that the current lagged the voltage, because doesn't that have a negative angle? And isn't that a negative angle? Still a lagging power factor, isn't it? Or that's still a lagging power factor, right? So I can't just look at the angles. I have to look at the difference in the angles. And is the current behind or in front of the voltage? Is the current lagging or leading the voltage? Clearly, it is, because when I look at the two, I can see, and when I draw my phasor diagram, I end up with a lagging power factor. Yes, sir.
So if the current's angle was like 31 degrees, then it would be.
Yeah, so for TV land, the question is, if the current was 20 at an angle of 31, what would the power factor be? I mean, would the power factor be lagging or leading? It'd be leading, because it's 31. If it was 29, it's lagging. Positive number, but it still lags the voltage. Okay. So again, I wasn't saying you guys were wrong. I'm just saying you need to add that additional part. So we got a lagging power factor, and that was indicative of these parts here. That's where I found that out, or I looked at it and I. So now I'm going to go ahead and calculate what the power conditions are. So my resistor is going to consume some power. I know that. And I can solve for that saying VR times IR, and I can solve for V, which is just voltage times current. So 4 times 20 at an angle of minus 6.9 is the voltage. Then I multiply by the conjugate of I, and the negative 6.9 and the positive 6.9 cancel each other out. So I just have 4 times 20 times 20, which is another way to say I squared R, right? And it's magnitude only I squared. So this equation here equates to P in a resistor is I squared, but it's magnitude of I squared R. And I'm highlighting that because we'll start to see where that's really important. But yeah, you get 1600 watts. Now I go ahead and do it for the inductor, and I can do the same approach, which I have VL times I. VL is 3J times the current, and I take the conjugate of that. So I have 3J times 20 at an angle of negative 69 times 20, positive 69. So again, the I, this here becomes the magnitude of I, doesn't it? Squared. But I have a J term over here. So that makes it reactive power. I have a J term. That equals 1200. Can anybody take their fancy dancy calculator out and tell me what 2000 at an angle of 36.9 equals in rectangular form? Nobody wants to do that? You'll do it? We'll do it together. What is it?
2,600 plus J12.
Is that what you got? About 1600 plus J1200 matches 1600 plus J1200. Conservation of power. The power supply from the power supply, 1600 plus J1200, has to be consumed by the load, 1600 plus J1200. If it didn't, you wouldn't have conservation of power. You'd be a mistake. So I actually didn't even need to do these calculations. I did just to show you, hey, this all checks out. But in reality, you don't even need to do that. You know that all the real power in the resistor is 1600 watts and the reactive power is 1200 watts. Okay? Yes, sir.
About the I squared, you say the 20 minus the angle times 20 times, and then the positive angle.
Yep.
What are you trying to do?
Because it's VR times I conjugate. And remember, VR is equal to R times I times the conjugate of I. And the conjugate of I is take the negative of the angle So when I take the negative of the angle and I multiply that with a positive of the angle, I just end up with that, right? It's just the magnitude only. The angles drop away. Okay. So I don't have to worry about angles there. I just have to worry about magnitudes. Does that answer your question, B?
Yep.
Okay. So I squared R for resistor, magnitude I squared R for an inductor, I squared R again for a capacitor. You just see the negative in there, which shows you it's going in the opposite direction of power, but you can see that from your power triangle as well. You can also do V squared over R, but again, it's V magnitude squared, not V magnitude and angle squared. And it's the same thing for V squared over X. The one that you'll be using the most is here, because normally you'll calculate the current and not the voltage drop. Those two are the most common ones that you'll use. All right, so let's look at an example. We kind of did a similar example to this yesterday. We have a load, 100 ohm resistor load, which is equivalent to, I don't know, a factory, because the voltage across it is 40 kV. And we want to calculate what the voltage at the source needs to be, including that voltage drop. And then we're going to calculate some power. So the first thing we need to do is calculate the current through the line. So we got 40K divided by 100 at an angle of 0, which is 400 at an angle of 0. Is Eli happy? Eli current lags the voltage. See how I flipped it for you, right? I didn't say percent. Now I'm using lag and lead. Current lags the voltage in an inductor. ICE, current leads the voltage in a capacitor. This is 0 degrees, which is what it's supposed to be because it's a resistor. It's neither an inductor nor a capacitor. So there should be no phase shift. So that checks out. Now I'm going to calculate my voltage drop. I'm going to calculate the source, including the voltage drop, which is 40 kV, which is at the source, plus my 400 amps at an angle of 0 times my line impedance. And what I see is that the utility has to set their voltage at 45 kV. They actually can't set that. But the reason why we assume that they set it is because we have to start from someplace. And since we know that's 40 kV, we just pick that reference at an angle of 0 to make our calculations work. Otherwise, we could never do the calculation. But in actuality, they're just going to set it to 45, and then the phase angle at the customer doesn't care what the phase angle is. They just care the magnitude of the voltage is. Now we do S equals VI conjugate, and we get 18 at an angle of 20 MVA. Okay. Now, you'll notice over here, there's no angle. Over here, there's an angle. Why is that? Because J40. That transmission line is requiring reactive power for this system to work. So my power triangle for my load is this. For the whole system is this. So I have to put some reactive power out on the system to be able to make this work. And that's exactly how it works in the real world too. You have to put power out. Now let's tweak it. Let's put a big old inductor in there. Now the load is no longer unity power, right? No longer at 1. That's another term we use, is unity a lot. So now we calculate the load, and now we can see that we've got 141.4 at an angle of 45, because the real part and the imaginary part are the same. So you realize that the 45-degree angle between the hypotenuse and the real part, which if you take the cosine of 45, you get 0.7. And Eli says it's a lagging power factor. So now my current was at 400. Now it's up to 565. So just by the addition of a J100 ohm, some imaginary reactive power, my line now has to be able to handle almost 565 amps of current. Which means I'm gonna get a lot more I squared R losses in my line, right? Look at the voltage though. I went from 45 kV up to 60 kV. That's how much voltage drop I'm getting across the line. So you can see why the utilities don't like it when the load is running at a 0.7 lagging power factor. They get really upset about that. They're gonna charge you a lot of money for that because it gives them a lot of agita. Not only do they have to run their generator, you know, at 50% over what the voltage would be, but they also have a lot of I squared R losses in the line, right? 565 squared or 564 squared is a lot more than 400 squared, right? So now look at the power. I was at 16.8 plus J 6.4. Now I'm at 17.6 plus J 28.8. So the MVA is not as big of a deal increase, but now I'm increasing the real power demand by 0.8 MVA, 800 kilowatts. Where does that 800 kilowatts go? Up in the air. I squared R losses on the line. So that is power loss. It's a big electric radiator. And that power isn't free. They got to pay for that additional 800 kilowatts of power. So you can see that's a really bad thing because now they're losing a lot of money. Not only do they have to operate their equipment outside of its its typical value, but now they have to pay the generator companies for 800 kilowatts of power. This is if you want to do something called a load flow. You can take a look, but essentially we're going to do everything as a single line representation, which this shows with that case where we've got 16 megawatts of real power load plus the megavar, and you can see the voltage at the bus is 40. You can see the direction going in as 16 minus 16 because it's going in the opposite direction. And then we can see the power, and then the load consumed is not here. Okay. Oops. So now if I put a capacitor bank on there, all that 16 megavar at the load is provided at the load, then everything goes back to a nice calm state. So you have to do a lot of reactive compensation if your power factor is low. And if you work at industrial facilities, they're putting cap banks all over the system to do that. In fact, how do you go ahead and do that? You can just do this calculation here. I know I'm running out of time. I've only got a minute, I guess, or I'm actually a little over, but you can see the cap calculation here. And here's a cap bank. It's actually out on a distribution circuit. So even the utilities themselves will put these out on the line. Okay, sorry for running a little late. Guess I got really excited. Any last minute questions? All right, have a great day, y'all. I will see you Thursday. Take care, everyone.
Thank you, Paul.